Simplicity. Style. Excellence. The Sony SOBAX ICC-1600.
What you see before you is a Sony SOBAX ICC-1600W, a calculator from 1973. This thing has every feature you could ever want in a calculator. We've got addition, we've got subtraction, we've got multiplication, and even division. Do you need to remember a number to use later? Well, forget about it, because the SOBAX will remember it for you. And those aren't even all the tricks this thing has up its sleeve. You can use this dial to adjust how many digits are to the right of the decimal point. It can go all the way up to 10 digits, and this is a 12-digit display. In addition to letting you change the digits behind the decimal point, we can also choose where we round. If we do a division here, we can see what our number is. Let's go ahead and store that. Now we're going to round at a lower point, same equation, and we can see that first digit is 0, and if we load the other one, we can see how it rounded. If we round at a higher point, we can do the same expression, and we can see that it rounded at the next digit. This calculator still has two more features that have to do with running totals. So if we press K, we can do 2 plus 2 equals 4 equals 6. 8 plus 6, 14, 20. That enables the continuation mode. Now that does not work. T is different. So if we do, say, 10 times, 2, we get 20, times 2, we get 40, close it, 60. So T runs an accumulator in the background that will add up all of the results of everything you've done. Here's something else interesting about the calculator. When you do division of long numbers, you can see how long it takes for it to actually do the calculation. Let's take a look at that in slow motion at 240 frames per second. As I've been demonstrating, this calculator is electrically fine. It does have one flaw, though. The change sign key does not come back up. The only blemish other than the malfunctioning key are the asset tag here and engraving here and here when this unit seems to have been owned by the Mountain Bell phone company. And oh yeah, this thing uses Nixie tubes. In case you're not familiar with what a Nixie tube is, they have filaments for each letter inside of the tube that light up to create individual characters, and they're all stacked on top of each other. Here you can see the internal construction of a Nixie tube. The numbers are individual elements that act as cathodes stacked on top of each other. Surrounding all of them is a mesh that acts as an anode. When a large voltage of around 170 volts is applied to a cathode and the cathode will emit electrons towards the anode. The tube is filled with a gas that reacts to those emitted electrons, causing light. Unfortunately, Nixies have an extremely high voltage requirement, so they're not easy to use. The Nixie tubes are obviously what drew me to this calculator, but it's pretty awesome overall. The ICC-1600 is actually one of several successors to an original calculator, the ICC-500. That one was released in 1967. Even though electronics were changing quite rapidly during that time period, this device still has quite a lot going on inside of it. So I think we should crack it open and take a look. Now they don't exactly want you getting in here, so they have these very weird security screws that I've only found I can open with these pliers. Fortunately, they're extremely well designed and these screws don't actually come out. They just stay in the plastic as you open the case. There are only 2 screws on the bottom here and here that hold this thing together. The rest of it is held in by latching it. Once those screws are off, you lift from the front and pull towards the back to remove the top. And you can see inside in all its dusty glory. There is nothing quite like the smell of 45-year-old electronics. Oh, that's the good stuff. Now, I don't know how willing I'm going to be to go any deeper into this. We have 1, 2, 3, 4 layers of circuit boards that still work and don't really need to be changed. I mean, yeah, it's pretty dirty in there. I could clean it up, but I don't really need to. I may also be a little hesitant to poke around in there, knowing that there's 200 volts flying around. This is unplugged, but there are some big caps back here. Oh man, it's so pretty in here. Look at this cable. This is wound with string around the wires. That's just crazy. This thing is just beautiful inside. Look at all those glass diodes. Wow. Now there are 2 reasons that I really want it in here. One is that these Nixie tubes are really, really dirty. And I don't mean a little dirty. Yeah, those things were filthy. I'm going to do something pretty stupid and try and blow this stuff out. So let's see how this goes. I should really do this outside, but no. Oh, wow. This is making a significant difference. And really messing up the air. Look at that. More string-wrapped wire bundles. That's just too pretty. I can't imagine how long this thing took to assemble. Look at this. Wow. I'm going to attempt to disconnect the keypad. Let's hope I don't regret that. Oh, there's more. Ah, yes, the AC power switch. That makes perfect sense. Ooh, it's keyed. That's nice. Okay, I've got both of these much cleaner now, and it makes me a little more confident in trying to poke around here. So let's try taking a deeper look. The first thing I should really take a look at is repairing the broken change sign key. So we're going to have to lift out the keypad area. Let's go ahead and do that first. And there we are. I have used most of the computers that came out after this calculator, and their keyboards don't feel anywhere near as good as this does. I would say these keys are most like the keys from a Commodore PET. They're definitely similar in shape, size, and feel. But these are just, they're better. I'm not sure what it is. It looks like to get to this keypad area, we're going to have to take out those 4 screws. So let's go ahead and do that now. Oh, of course, I've had my white balance set wrong this whole time. Apologies for that. Let's get these screws extracted. Now, the only way I'm going to detach this component is by desoldering all these wires, and that's not happening. So this is as close as we're going to get. We can see the springs that wrap around the keys. I might be able to just pull it up, but I don't want to break it. So let's go ahead and... Oh man, I have to remove all of those in order to get to it. I expect this to be very similar to the Commodore PET keyboard and have interleaved pads on the other side of this PCB that are contacted with a carbon-infused rubber pad, and that's how contact is made, unless this is different because it's slightly older. which could be the case. The worst possible case here is that this is more like a TRS-80 Model 4, where I will have to desolder all of these, which, now that I'm thinking about it, those are solder points, and Commodore PET keyboard does not need solder points. So I'm very afraid I may have to solder this, or desolder these to get to that. In which case, I may try a bit more vigorously to pull the key from the other side. Because now I'm starting to suspect this may just free the black block under the keys, and it'll just wiggle around instead of pull out. I think this is the final one. Let's see what happens. Oh, whoa. What do we have going on here? Okay, I'm going to get to how these switches work in a moment, because they're whoa. But for now, let's go ahead and take a look at solving this. So this is just one solid piece of plastic here. All this does is have the actual physical movement. So most of the other keys work just fine, but I can start to see some cracking around these. So as time goes on, these may start to deteriorate. It looks like the clear key may have cracked nearby, but near the edge there, here, but I don't think that's really the problem. It might just be dirty in there, so let me try clearing it out. Boom! Okay, so let's go over what I did here. This piece does not contain anything electronic. So I took it under water and tried rinsing it out while pressing the key repeatedly to try and clean out the contact areas around that, and it didn't work. So because each one of these cylinders is independent of each other, I was able to blow into this key and press on it repeatedly, causing pressure to push the key back out, because I believe this is a rubber seal right here formed for I don't know why. I think I may have an idea when I will look at in a second, but I was able to use that to push the key back out, and maybe I pushed through something by blowing air through it that cleared it out, or maybe repeatedly pressing it over and over again cleared it out like I originally thought I might be able to do. But either way, this now works. So adding air pressure to the back of this, while wet possibly, may be the fix for these types of keys. Modern cheap keyboards use a membrane with two pieces of plastic that contact when something pushes them together. Mechanical switches use some form of levered action to physically press down two pieces of actual metal. This is different. These are reed switches. They are activated magnetically. Let me bring a microphone down here and show you, because I can activate them by moving a magnet over them. So yeah, those are pretty sweet. That's cool to see a different design like that, entirely from what I'm used to. Now the key block, I guess it would be called, is still drying from having water on it. So I'm going to go ahead and set this aside, and let's take a look at the layers of circuit boards in the calculator. From what I can tell, it looks like these two screws are the keys to the city. So let's pull those out and see what happens. Success! The part is removed. The way that it works is it has these hooks that you have to slide over. So this goes in, and then you pull it to the right to lock it. So you have to pull it to the left to unlock it. But we now have access to these circuit boards and can continue the disassembly and admiration of this wonderful calculator. From here I should be able to just slide out the individual component boards. So let's give this a shot. Use a screwdriver in the back to gently wedge them. Yeah, that'll work. Perfect. Excellent. We have the display board. Logic board B. Logic board C. Oh, you know what? I think I need to take this the rest of the way out, which I think will now just slide forward? No? Lift? Aha! That cable's holding me back here. There we go. Ah. Okay then. Logic board C. And the final logic board. Here you can see we have this massive backplane PCB. I'll get a shot of it at another angle because it's got a lot going on back there. Or should I just remove it? I think I can remove it. Let's do that instead. Now just disconnect it from power and it's loose. Look at that. Man. And that is all there is to the power supply. There's a couple of bulk capacitors down in there, but I don't see a reason to take that out. That all works, so I don't want to touch it. So here we can see the 4 circuit boards that make up all of the logic of the calculator. Also, you can see that these 5 tubes have had the majority of the wear on there. The previous owner probably had this set to use 5 decimal points of precision and to round off the last 2 digits. This darkening is called sputtering and happens when the tubes are used for extended periods of time. I've been looking at these boards trying to figure out what each one does, and I'm still not quite sure. The vast majority of the parts on these are actually manufactured by Sony themselves, so they haven't really taken the time to label these in a way that we can determine what they are. Trying to look up the data sheet for, say, this Sony 5010C, maybe OC, I can't find anything, nor with a 501OD, or a 50401, a 509OH. They're not the typical logic chips that you would see, like, say, in that Commodore PET. We can attempt to guess at what type each chip is by looking at how it's laid out. The sheer number of 501s, for instance, scattered throughout all of these boards makes me think that they may be some form of memory. Now, thinking about how the calculator functions, it has one register for input, another register for input, one register for storage, one register for the result, possibly, and then one accumulator register. So it could have up to 5 registers, but it's most likely 4, because the result is most likely put into the first input register. I also find it quite interesting how few differences there really are between the boards. They're all the same types of chips laid out in the same types of ways. There are only so many things they can do because this has a horizontal layout on the top and a vertical layout on the bottom, which makes sense. But it still seems to be vast majorities of 501s. Like, this whole row here is nothing but 501s, 501s, so that is very likely a memory bank. But it's still difficult to determine how this works without being able to get data sheets for these parts. One interesting thing about these boards is most of these are like this, where you can see exposed copper traces. Only this one seems to have been tinned on all of the traces. I don't know if there would be a specific reason for that. Some models of these calculators I've been able to find online actually have full solder mask circuit boards, so it could just be how the production was handled that day. We can see what are most likely the individual transistors for driving the cathodes of the Nixie tubes, and how everything is vertically constructed up from the board instead of horizontally to get as much on there as possible. I really hope I never have to try and find one bad part on this device. Finding it won't be easy. Getting replacements will most likely be impossible if it's one of the chips that has gone bad. Well, I think it's time to go ahead and reassemble the calculator and test out our keypad repair. Now that the display has been cleaned, those numbers are way more vibrant. Now that we've got the Nixie tubes clean, let's go ahead and get a macro of them running. Yeah, those are really cool. One more time. Alright, one more time, but without lights. Well, I think that about covers the SOBAX ICC-1600 here. This is definitely one of my favorite pieces I've added to my collection now, and honestly, it's one of the most practical. I can still use this every day. This doesn't have to just languish on a shelf like most computers I get do. This can just easily fit under one of my monitors. Just pop it on, do some quick math, shut her off, good to go. Now that I've seen that the Nixie tubes are likely powered with 200 volts, I didn't measure that. I would know that that's overvolting these, and I probably don't want to have this be running all the time. I was thinking it might be fun to modify this to show the date and have a clock if I had a certain key combination pressed, because I suspect that other connector over here would allow me access to the registers to the display. But I really don't want to burn this out. This thing works, and I want to make sure it stays that way as long as possible. Well, I hope you've enjoyed this extremely awesome look at some old technology. I'll see you next time.